Hello, everyone. Welcome to DVCon Europe 2020. This is about the panel one sessions today. I am Chuan Nguyen. I'm the panel chair of the panel session in DVCon Europe 2021. Today, we have a discussion about anatomy of a verification flow with Jean-Marie Brunet from Siemens EDA as a moderator, and we have a lot of great people here from AMD, ARM, C5 and Mythic AI to debate and discuss about this great topic of verification flow. For any question that you may have, this is a pre-recorded sessions. So during the sessions, you can put questions via the chat. And if any panelist is online, he can answer. Otherwise, you can put it on a virtual platform and we can reply later on asynchronously. So today, Jean-Marie will moderate the panel. So Jean-Marie is Senior Director of Product Management and Engineering for the Scalable Verification Solution divisions. He has served for over 20 years in application engineering, marketing, and management roles in the industry, and have an IC design and design management position of ST Microelectronics, Cadence, and Micron, among others. So Jean-Marie holds a master's degrees in electrical engineering from ISEN Electronic Engineering School in Lille, France. So I leave it to you, Jean-Marie, now to start to introduce our panelists and start the discussion. Thank you.
Thank you very much, Tran, and thanks for the opportunity to moderate this panel. My name is Jean-Marie Brunet, as Tran mentioned, and we have 4 great panelists today with us. First, Alex Starr, Corporate Fellow from AMD, based in Boston today. Daniel Schotstack, who is an architect and fellow in verification at ARM, who is based today in Cambridge, UK. Nasrullah, who is Sci5 Senior Director, based in Austin. Ty Garibe, who is VP of Engineering, Vice President of Engineering of Mythic AI, based in Austin as well. Thanks everybody for joining me today. The topic of the panel is anatomy of a verification flow, and we have prepared some questions that talk about different subjects that are important in verification flow nowadays. So I'll ask each of the panelists in the order that you see here from left to right to start, and after that we'll have an open dialogue. So I'm going to ask you to describe what is your must-have verification tool, and in your estimation, are these tools applicable to all market, or different market require different tools based on the type of design that you are doing, being either IoT, AI,
panel, and great to see a lot of fellow folks here as well. So hello to everyone. So yeah, in terms of the must-have tools, I think from an AMD perspective, we see RTL simulation obviously is a big one, and that's been a staple for many years. I think despite the increase of compute power that we see in the industry in terms of server capabilities, the industry is generally struggling for to contain all of the verification needs within the scope of an RTL simulator. And so we definitely have seen an increase in emulation and prototyping over the years, and I think that's not a shock to anyone. It's clearly been a growing trend, and something that's rapidly increasing, I think, as time goes by. I think from a different market perspective, we have companies that have very large designs, and so they require a certain type of hardware emulation solution. And I think other areas of smaller IPs, smaller designs, maybe don't need quite that amount of capability that some of those larger big box emulators require. And I think that there's opportunities there in the sort of prototyping space and some of the new technologies coming out in the prototyping space that can really address that. So if I think about the must-have verif tools, I would say RTL simulation, hardware emulation from small design up to very large multi-billion gate designs. And then I think what I'll call enterprise prototyping will additional FPGA prototyping smashed together with hardware emulation toolchains to create a much more usable and scalable FPGA-based solution. And I think that's something that's been emerging in the last year or so, and is really really attacking the kind of needs of the market and the industry. So that's very exciting, and I think is now becoming a must-have tool. I left out formal verification, of course, which I would be remiss in not mentioning. That is clearly something that's on the increase as well. It has been for many years, and is an absolute staple of how we do verification.
Great, thanks, Alex. Daniel?
So I think Alex has covered pretty much everything I would mention, including formal verification, which I would have thrown in if he had forgotten that. And I think there has been a step change in what formal verification can cope with and different usage models, but it's still not to the point where we can discard simulation or not have to worry about emulation on FPGA. So I think it's not a question of there's just one tool one must have. There's a range of tools that help you address different areas, and at the moment they're fairly complementary. In terms of the different markets, I would probably throw in that depending on the market, so if you're looking at, say, healthcare, then you're going to be thinking about the sort of functional safety or the security aspects of things, which then often pull in other specialized tools on top of the standard, what you get with simulation, formal or FPGA and emulation, which we've been doing for a very long time.
Thank you. Nasser?
So hello everybody, my colleagues here have mentioned all the various things that they've covered the spectrum. I will add to that to say a few things. We're having to use Verilog simulation and emulation or FPGA quite a lot together to do a lot of our verification, whether it be functional verification or performance verification. So one of the important things that is coming up is scalability. We're finding that our needs scale up and down. And in the traditional days, we bought a emulator from one of our favorite EDA companies and had one box and then had to bring in another box. There's a lot of infrastructure needed to put all this together. So having a solution where there's scalability, where we can go up or down, is very useful without having to get a whole new factory to set up things. I remember in my Samsung days, it took a few months for IT to get everything in order to get a new box in. So I like some of the models that are coming up, like the one at Amazon Web Services, where you can get more and more FPGAs. And I encourage all the EDA companies to go to some sort of model whereby we can do a lot of scalability. So with that one thing being scalability, there's also interoperability. We use things in RTL, we do things in emulation, and we see problems and we want to bring it back all the way to RTL. So having a good mechanism to go back and forth between that and simulation, whether it be C level or RTL level, is important. And the third thing I'll mention is something that we all use, our favorite test case generators. Very important. But I think we need to go a little bit beyond traditional test case generators and look at things that affect the system side of things. And I'll give one example from my experience back in the Motorola days. I was a happy young apps engineer over there, and the Navy came and their F-18 simulator was crashing after the pilot did a 7-degree turn. Apparently they turned 7 ways down to escape some missiles or something. On the 7th one, it crashed. And this came out because of the interrupt handling, nested interrupts. How many test case generators check those things? So there's a lot of system level things that it would be nice to have very flexible test case generators to be able to look at some of these things that we don't traditionally look at unless there's a problem. So those are the things I say. Thank you.
Very good. Thank you. I took notes, so we'll go back to a couple of your points. And Ty, please.
All right. Oh boy, it's tough to go last on some of these. Being that we are at Mythic, we're developing a AI accelerator, so a separate chip that is intended to be mated with a host, and that a lot of what we're doing relies on analog circuits to implement our functionality. I would highlight two tools I haven't mentioned yet that are important to us. One is the ability to model the system. So virtual platform modeling, QEMU, and other types of acceleration so that we can see the interaction of our chip with a variety of hosts and debug our firmware and drivers. So that's a critical aspect of getting our product ready for integration into our customers' products. And then on the other end of the spectrum, we require the ability to integrate some level of analog real number simulation with our Verilog. It's very challenging, and I think it's probably better now than it used to be, but it's still very challenging. And I think it's an area where we would certainly appreciate better ways to do it.
Very good. I got the message. I think the industry got the message. Thank you. So let's zoom a little bit on the hardware-assisted verification and how it evolved over the years. I think all of you touched a little bit on this. We see more and more pre-silicon verification, validation done with hardware-assisted verification in general. Do you see additional trends? And we have seen recently that there is an announcement on, from different vendors on virtual platform, hybrid verification, which is enabling shift left really a lot sooner. What else do you think is missing in the verification and validation flow that is not being discussed today, or highlight what is being discussed today that is done well and quite effective for you? And no specific order, so whoever wants to talk first, otherwise I will pick.
Well, I'll go first. I mentioned this already in my talk about scalability. Okay, we're at the point where,
what you mean by scalability, Nasser, please, so it's clear to everybody.
Back in Samsung, as every time a performance team, I'm a part of the performance architecture team, and in Motorola, every time we're successful in running things very well before tape out. We always got requests to run more and more things, bigger and bigger things, more and more cores, all of that. So I would go off to my favorite EDA vendor and say, yeah, we need some more. And they'll say 3 months to install it. IT will say another 3 months to put air conditioning and space and all that. You have to wait about 6 months to get it up there and get things working. That we are now, everything is getting faster. The phone, all the cell phone providers, you get a chip out every year. You can't wait 6 months to get your infrastructure and things in place. And unless you have very big budgets where you have all of this planned out, there's so many startups and fast moving companies, we have to be able to move faster. So whatever mechanisms the EDA companies can use to allow us to move faster. And one thing I've advocated all the time is you have a subscription model that we can keep on buying more and more of your boards or your FPGAs or whatever we have to increase and decrease. So we don't have to go pay the air condition costs, the factory costs and all that. Okay. That's key importance. I like the hybrid approach, and I believe we have some questions on hybrid where we can move back and forth. You have to essentially move back and forth between C-level simulation, Verilog, and emulation, whether it be FPGA or standard emulators. And back and forth means different things. It's not just taking an FSDB and then porting over. It says a quick, easy way, push button way, where we can find the code we're interested in. We used to look at things where we had high power spikes. I want to be able to focus on that piece of code and then quickly move it over to my RTL to see what's happening. I don't want to have to go through a lot of development of tools to get that process planned out. And I think the EDA companies play a big part in this to make that flow seamless for all of us and quick, because we need to do things fast. Things are happening way too fast in this world. Thank you.
Anybody else?
Jump in, not last on this one.
Right.
Yeah, definitely. I think we're seeing a lot more hardware-assisted simulation as part of the shift left. But interestingly, I see it as also a symptom of the AI nature of the business nowadays. AI applications are inherently large. It is really difficult to simulate anything AI quickly. So there's no small benchmarks. There's no doing a whole frame of any network is a lot of compute, and it takes a long time to run in any simulator. Doing 100 frames, 1,000 frames, however many frames you need to validate your network performance in simulation takes a huge amount of compute power that is generally beyond the Verilog standalone. So I definitely see that the fact that we're building max size of the reticle chips with 20 billion devices that are also running very complicated algorithms that take many cycles to get to even the first output, is all coming together to drive a need for more and more hardware-assisted simulation. It's great for the box providers, and it's a challenge for us to integrate. The way Nasser has said, you got to plan ahead, and if you miss, boy, it's tough, especially with the lead times that we're seeing in our industries today.
Thanks, Ty. Danielle or Alex?
So I think there's so the use of the hybrid emulation and models like that, it suits some purposes better than others, because one of the areas we use it inside ARM is for effectively testing of our GPU drivers, because we can use the CPU in a virtual platform mode, not have to worry about running Linux or anything else to actually base the drivers on. And that's all predicated on there being a long pipeline in the GPU and not requiring a lot of interaction back and forth between what's in the hardware and what's running on the virtual platform. So one of the things you asked was what is missing, and I think one of the bits that is missing is if you're sort of scaling more traditional CPU IP where you've got a lot more interaction and it's a little less fire and forget, as it were, then it's difficult to think of ways of putting in sufficient buffering between the virtual platform and the hardware that you don't end up slowing down the hardware, essentially.
Good point.
Yeah, I think I've gone last this time just to give everyone a break. But yeah, all excellent points. I think to touch on Naz's comments about scaling, certainly we see that, like as mentioned, with the supply chain challenges right now. That's obviously challenging for us getting new hardware emulation capacity in. But I think one thing that is for sure is that the dependency on emulation is now a little bit different than it was, I would say, maybe 5 years ago. And I think it's absolutely critical now for any of our products, I would imagine, that we have to go through an emulator to get to tape out and have confidence in the design. And shift left is a thing we say, but it's a thing we need to do to hit the market windows. Right? It's absolutely baked into the schedules. So this becomes challenging when you're approaching tape out and you realize you wanted a whole bunch more verification in a certain specific area, and you've got other programs competing for that hardware resource. That's a challenge. You need to have an opportunity to turn the knob up to 11 for a little bit and use more capacity at a short amount of notice. And so I think as an industry, we need to figure out how to do that sort of cloud model, burst model type of approach. I think that's something clearly that the industry needs. Yeah, so I think that's on that topic. I think on the hybrid side of things, we've been doing hybrid for a long time, and it's just it's sort of exploded in every dimension. Really, it's lots of hybrid models anyway, and I think the motivations behind that are trying to get the most out of the capacity you have. So you're not putting everything into an emulator or a prototyping platform when really you're only focused on, for example, in the ARM case, the GPU. We do similar thing where you put the GPU in the emulator, and the rest of the subsystem and the SoC is modeled on the real hardware, sort of server chip attached to the system. So we see that in all kinds of different areas, and I think one of the challenges is working out what kind of test plan you're going to do in which environment, and which ones are better for certain environments and others. The power and performance is a big growing area that we're seeing more and more of, and that brings with it a set of constraints that we didn't have to worry about when we weren't looking at power and performance. Latency, bandwidth, you want to be able to measure things accurately and understand whether you believe the results or not, and how do you get confidence in those results without having to emulate the entire massive AI chip like Ty was mentioning, right? How do you do that? Very challenging. So, you know, I think that's one of the challenges we all face, and you know, we all have our own special ways of trying to deal with that. So I think that's a big interesting area. I think also we're seeing an evolution of, you know, certainly in AMD, when we started emulation and prototyping, we were looking at what can we do that is going to help us get our product out to market earlier. So we had verification teams doing a whole bunch of stuff on RTL simulation, and then we would do emulation and tackle some of the post-silicon challenges that we would see, and see if we can get those all cleaned out pre-silicon and get our chips out earlier. And absolutely, that's a huge piece of what we do still today. Absolutely, you know, critical. But we're also seeing a migration now of things that the verification teams really wanted to do in RTL simulation, but really they just practically can't do that because the cycles per second of the simulators are too slow. So we're seeing this migration of verification workloads over to the hardware assisted platforms more and more. Year by year, we're seeing more and more of that. And so that they actually, you know, in some cases they require different approaches and the way you construct your environment on the systems to do that. So I think that's another evolution we're seeing. I think in terms of what's missing, I think Ty already mentioned the analog modeling component, and I think as companies have more and more multi-die designs, suddenly you have analog components in the critical path of bring up, initialization, reset, etc., which is sort of the first thing you do out of the gate in a validation program, right? And suddenly now we've got these analog components in that path, and more of them. And so making sure that those are going to come up very quickly is very important. You know, it's almost like the logical piece of the design. We've got a story on that. You know, we know how to do that. Okay, and yes, we can get better at it always, but we have a story on it. But the analog piece really is very challenging, especially its interaction with firmware running in this large system. So yeah, that's a piece that we're missing. I know there's work being done to look at that, but still some work there to be done.
Okay. Yeah. Jean-Marie, if I could touch on a point that Alex raised that is important, especially to those of us that are doing highly iterated tiled type processors where a lot of the functionality is very similar across the entire die. We spend most of our simulation time at the tile level, verifying the heck out of that. We integrate it and we hope it works for the most part. One of the challenges that I'm finding with hybrid simulation is the inability of the test benches, especially UVM, to scale across the full range of new validation options. And so you find yourself having to make a choice. Am I going to invest in a test bench for every level of my design, for every simulator that has a different style of interaction? Or do I pick and choose where is the value going to be greatest based on my staffing and the familiarity of my staff with each of these tool flows? Clearly that's an opportunity for improvement going forward to enable a lot more hierarchical reuse across different types of simulation platforms. That would, I think, be very useful to a lot of people.
Okay, good, thanks. All right, related to scalability, I think this is a question that is always very like a hot topic in my team. So I'm gonna raise it with you guys. I see a lot sometimes companies saying, I have 10 billion gates or 15 billion gates. And to me, there is a very big difference between emulating a design that is 10 billion gates, which has a challenge of being able to compile and run such a beast, such a large design, and run complex workload on something that is 10 billion plus gates, versus managing a farm of 40 instances of 250 million gate type of design. And I'm not saying one is easier than the other. I think they have different type of challenges. And I like to hear your different perspective on the different type of challenges based on the two buckets here. And is this addressed well for both of those spectrum in the market today? And what are the challenges that you see? No particular order.
I'll start with an interesting artifact that we see, and that's scheduling jobs onto the systems when you have wildly different sizes of design. So, for example, if you take a 5 billion gate design, let's say, you schedule that, and you're taking the place of many smaller jobs that could get on there. And maybe those smaller jobs, you have a batch scheduling system that you submit, and they get onto the system when they can. And then the problem happens is when you get off the system with your 5 billion gate design, all those small jobs get, scatter all over the system and they're running. Now you want to get that 5 billion gate job running again. Well, you've got to displace those smaller ones, or do you wait for them to finish? Or, you have to have a whole system for managing how you ensure that you get an allocation for a particular program that's got a certain types of build sizes, and how do you also have a scheduling system that is going to honor the sort of priorities of those programs and give a fair usage. Because obviously, while you're sort of draining the system for that 5 billion gate design, there's capacity not being used there, which we don't like. And so how do you actually manage that? And so, it leads you down lots of different avenues of how you can deal with that, whether you dedicate systems for, this system over here is just going to be for the really big designs and nothing else. And so everything tessellates nicely. So it's almost like you're kind of playing Tetris in your head, and in an efficiency algorithm, how you decide which jobs are going to go to which systems. And when you have a lot of emulators, that sort of becomes easier in some ways, because you can say, well, these ones are the big ones and these are the small jobs. But if you've got a smaller number of emulators and you've got this big difference in design size, then you're getting into low efficiency territory, which we don't like. So yeah, that's certainly a challenge from that perspective.
Alex, I hate to burst your bubble, but you will never have enough emulators.
There's never enough, that's true.
Yes.
That's not a bad problem. I'm okay with this problem.
You guys need to come to my side of the street. We have one.
So you know what I'm talking about, Kai, with the big and the small jobs. Yeah.
But I want to add something to what Alex says, very important. He talked about the scheduling aspect of that. And a lot of us, a lot of companies, they don't think about that, because sometimes the size of the team you have to put, the people you have to hire to put these good automated schemas in place is a very different skill set than whether it's verification or performance. You need some people with good software knowledge and who understand the hardware. And this is infrastructure. Infrastructure is becoming very, very important. Yeah. And Alex's point is well taken. You want to use every of these expensive things, you want to use every ounce of it, and you have to have a very good mechanism. I mean, there's lots of research on scheduling stuff all over the place in all kinds of areas, operations research and all that. You need these kind of people with that kind of skill set to be able to do that.
Yeah, and I think Nazar, the emulators have their own special quirks and features, right? Which software like scheduling, RTL simulation jobs is such a piece of cake compared to trying to schedule emulation jobs. It's not even funny. I mean, all sorts of interesting rules that different types of emulation technologies have about what can go where and what can't, and those kind of things you have to keep in mind when you're in a job scheduler to get high efficiency. It's a very complicated problem.
Right. So if your EDA companies have big infrastructure teams that can do this well, we'll all be so happy. But I would like to bring up another point on the size of designs. Our designs are getting bigger, much bigger, and we're going to end up with a problem of them fitting in FPGAs. FPGAs are increasing, yes, in size, but I don't know if they're increasing fast enough. At least I don't think they are, because I'm running out myself. And I think one of the biggest things that will come into play, and some companies have done this well, is partitioning a design across multiple FPGAs in such a way that we don't get a big degradation in speed. And that is going to become critical in the future.
Yeah. Daniel, any comments on size?
Sorry. Again, I think if we look at some of or most of the big chips are iterations of basically much smaller subchips, right? There's maybe a couple that are not quite as regular as that, but most of them are, and so almost everybody has both problems. How do I verify the heck out of a significant complexity design, but that's still in the less than 1 billion gates easily? And then how do I get that final integration verification of the whole thing? And how many cycles really can I afford to do at that level versus how many do I think I need in order to have a quality product? So that, to me is the art still of the management of verification. How do you work with your team to understand their concerns? Oh my God, you're only going to give me the ability to simulate for 4 weeks at the full chip? I mean, how can that work? Well, okay, then we got to plan it, break it down, make sure all the interfaces are regular, standard, and tested, and so that when we snap it together, there is a viable chance that it will function well right off the bat. So that's to me the challenge of architecture, to enable verification such that we minimize the need for billions of cycles of verification at that massive full chip level, because you just can't do it.
Ty's point is good. We'll always miss things, okay? And I'll give you a small example of where I know I missed something. Are you all familiar with the Iridium satellites? 20 years ago, I think. There were the satellites that circled the Earth, and the first Motorola satellite phone was based on them. Mm-hmm. You familiar with those? Mm-hmm. You all know what happened to the Iridium satellites. They started falling out of the sky. Okay. The Iridium satellites had a PowerPC 603 in them. And I was the lucky apps engineers to talk with the NASA engineers about the Iridium satellites. And I remember sitting down in the meeting with them, and they're telling me, well, we have gamma particles and alpha and beta particles hitting those things all the time. And I'm thinking, we never verified for this. We never verified for all these changes. There'll always be something we miss. So, and we missed that, and the satellites fell out of the sky.
The end. Okay.
Daniel, anything to add on this section before we move to the next one?
I think just add a quick comment where people have talked about the scheduling difficulties with emulators. I think that's exaggerated when you move to FPGAs, because FPGAs are even less flexible in how you can recombine them and everything else. So I'd agree that the scheduling problem seems to be a common industry-wide thing that at the moment individual companies are trying to solve by themselves, rather than there being a sort of generic solution that people are able to deploy.
All right, now next subject is something that I think two of you have mentioned already on so far on this panel. And it's something that I personally spent time on since 2017, 2018, which is trying to put an emulator on the cloud. And we worked on something, I think, at DAC 2017 with AWS at that time. It's very different to put a custom hardware like this on a cloud environment versus, I will say, a simulation that you found out of CPU that would be in different location. So, and if you look at what the three vendors really are doing, is they call it cloud, but this is basically making infrastructure investment to make capacity available. So what's your view on the cloud access for the hardware-assisted verification business? Is this ahead of what you think it should be today? It is behind where you think it should be? Or you understand the complexity associated with this, which is this is not something that we put easily on the cloud? What's your view?
So, as you know, Jean-Marie, I've got views on this. I think the industry, we're way behind where we need to be, and that's pretty clear. The question is, how do we get there? And one of the challenges with putting hardware systems in the cloud is just the capital expense of those hardware systems, right? And there's a function of how long a provider would want hardware sitting unutilized that they can't generate revenue from, and that's ultimately where the difficulty comes down to, because I think otherwise, there's the scheduling aspect we just mentioned. I mean, that's clearly a thing. There's the security and data partitioning piece, which these are solved problems in the cloud world. So I think we should have a path there. I think once if we look at the rate of expansion of the hardware assisted verification segment of the industry, it's growing very rapidly. I would like to think that in the next few years that the industry is going to be at a scale where it sort of makes a true cloud-based offering a little bit more tangible and realizable. Because I think, like you said, it's almost like a co-location facility, the offerings that are in place today, which is sort of one step, but being able to dynamically burst capacity requires there to be capacity there ready to go at a moment's notice that is effectively not being utilized. And so being able to dynamically do that and keep all the data security and the hardware sort of secure and the revenue model of it being available that's the challenge.
I think you're right on the mark there, because it's a chicken, it's always a chicken and egg problem. There's not enough business to justify installing the infrastructure, but we don't have infrastructure, so therefore we can't book business. And so to me, it comes down to a business model issue, which is not that different from the rest of EDA in the cloud. How do you bill for it sufficiently to justify the investment in allowing customers to have a piecemeal type approach, as opposed to what we do today, which is we buy way more than we need so that we have enough when we need it, right? And that's the fundamental business model of EDA. Okay, well, that works, but that's the exact opposite of cloud. And so to me, there's a fundamental divergence there, and it's really hard to see how one company can do both business models. I could see a startup EDA company coming up and saying, we're all cloud. All of our revenue is cloud. We're going to do cloud. That's all we do. But to see that, it's really, we're in a oligopoly now with the majors controlling everything, and that's great. We get great tools. They have enough internal revenue to continue to generate, to invest and do research, but there's not that much diversity anymore, and this is an area where we could really use some diversity.
I think that the model we have now needs to change. We have to go to a cloud-based model. That is critical, it is essential, and I believe that there is a business model for that. And let me explain why I think so. There's a lot of many small companies coming up, lots of startups building IP with chips, especially with RISC-V, lots of them. Okay, these companies are not going to be able to afford these huge, big EDA transactions. Even Ty, you're saying you guys have one emulator.
Hey, don't pick on us, man. Let me feel bad.
But
they have a good one.
I had one.
We only have one.
We need to have something to go to. Okay.
Mm-hmm.
I see for cores. I had 100,000 cores, and we had in Samsung Austin R&D Center. It took us 9 years to get there. 9 years. Okay. Companies don't survive nowadays for 9 years. We have to have a mechanism to scale up. And right now, Amazon, Google, and a few others are providing this mechanism for cores. You want to get more cores. Amazon started with FPGAs also, and it's working somewhat. It's working good. I don't know how easy it will be to go to an emulator, but they're doing it with FPGAs. They're putting all the things in place. And you do have a subscription model. People can get it on demand. People can get it reserved. People can get it different mechanisms. And it's packed. It is packed. So there is revenue coming from it. Is that the same amount of revenue? I don't know. But it has to be cost effective, but there is revenue. So anybody can go off and do some design and go try to on an FPGA without having to build all this out. I think this has become very essential and critical. And I hope some of these big companies get together or figure out a way to do that for emulation, whether it be just FPGA-based emulation or otherwise, because this is becoming very, very critical now. So I'd like to add one more thing to that aspect. I think I might have mentioned that the partitioning across designs. I know Mentor and Synopsys and others have that. AWS, for instance, doesn't have that, but because there's more work for them to do that. But enabling that also is critical, I feel. So one of you guys can go off, make another startup, and go do that.
We might. Daniel, any comment on the cloud discussion?
I'm wondering whether some of this is about building up a backlog of sort of old technology, because for most of the times, if a company is buying emulators, they're going to buy the best emulator they can and use it for as long as they can until it's no longer doing the job it needs to for the size of designs they're creating. But if you're thinking of the world of startups, then that actually might provide a use for the older emulations. If the small startups are targeting smaller designs or more niche designs, then that way you get a bit more return on the capital than you would get just selling it to one company that's going to use it for a bit and then ask for a newer one, and then you've left with the problem of what do you do with the old emulator.
It's a great idea. Boom, there you go, Jean-Marie.
It's recorded, so that's great. I remember what he said. I guess I give you my view on this because most of you know we spend a lot of time on this. This is not really a technology challenge at all. This is purely a business challenge. And I don't want to open another conversation, but at some point, a lot of people are talking about RISC-V because they don't want to pay anymore for ARM and so on. I'm not going to open that here. But, you know, it's a fake argument. You know, there's no free lunch. And if people think they want to go to the cloud because they think they're going to spend less, I think you should study how it is implemented today. Maybe not in our industry, but the industry that have gone to cloud, they pay more because of that flexibility. And for certain business consideration early on when you start a company, it is very attractive because you do not have this CapEx investment to do upfront, which is very expensive for anybody doing semiconductors. So they think about OpEx, and at the time it's probably cheaper, but in the long run it is not. And that business argument, that business discussion is the most difficult discussion to have, particularly for hardware being on the cloud. Now, the example, Nasser, that you have referred to with Amazon with F1, for example, is very interesting because if you look at the pricing, there is a curve where it's attractive, but if you use it a lot, it's no longer very attractive financially. Mm-hmm. And that is the core of the conversation. If you really want to start to do it, you need to have the mindset of what is your end goal. So technically speaking, this is not a challenge. Of course, there is the differences between virtual and ICE. You know, if everything is virtual, you can virtually remote access and partition your design and so on. As soon as you have ICE, well, you need a physical connection. Somebody has to be next to the machine. Otherwise, it's not going to work. So there is some, I will say, physical consideration to review, but it's not. This is not breakthrough technology. There is some constraint of a piece of hardware needs to be close to the server because otherwise you get bandwidth problem and latency of the data. But it's really fundamentally a business problem. That's my view. I don't know if you guys agree.
I think companies do not look at the complete cost. Okay, for us to set up our emulators in Samsung and all the extra cores and everything, we had to get a whole big factory out near the airport. Huge empty building, and then you have to pay for air conditioning, permits, all that, power, everything, and security, of course, all of that. You know, if you look at all those costs, and then the IT stuff, 20 IT people to work on it. Look at all that, it becomes a more cost palatable solution than saying, oh, yes, if you have scalability and flexibility, it will cost more. But if you take the total cost, it doesn't come out to be that exorbitant or not.
Yeah, I think it's an economy of scale as well. If you go in, you go in completely. If you go in just a little bit, this is unsustainable. That's my view.
Got it.
Anybody else? Any other opinion on that topic?
No, I think we all agree it's just a business problem that you need to fix, Jean-Marie.
Okay, I'll take as an action item.
It's all on you.
It's a small action item to take, not a big deal.
The only thought I'd add is that several people mentioned that when you're buying hardware or slots for on-premise, you have to over-invest for all of your peak periods, whereas cloud does give you potentially the ability where you invest for what you need in general, and then you can burst for the peak when they occur. And I think that's where it becomes very attractive.
Right.
Definitely, good point, Pim.
Yeah, I think there's the technology refresh angle as well to cloud, where, you know, if you purchase your own system, you've got it forever, and it's using up lab space and AC. To Nazar's point, all these things cost money, and once it ages out, you're still using that lab space and still, you know, using the power and the cooling. And so, you know, a cloud-based offering has the ability to say, you know, here's some pricing structure, but you're always getting the latest and greatest technology, and especially in this, you know, segment of the industry where it's moving so quickly, and we're turning around new types of systems, fairly frequently now. I think that becomes an attractive thing around cloud as well.
Agree. So maybe it's another topic for another panel about how ED industry is reacting to putting hardware-assisted verification on the cloud. I think we're on top of the hour, so we're probably going to end the panel.
Jean-Marie, your voice cut out.
Sorry? Sorry, can you hear me?
Yes.
Okay. Sorry, I said we're on top of the hour, and I think we are going to have to stop here. I wanted to thank all of you for spending the time on this panel today. I know you have a very busy schedule. I appreciate the time you spend with us. I really hope that we will have an opportunity to see each other soon face to face. I hope you can hear me. I think Nasser is saying that my voice is being cut out, but
I can hear you fine.
Yeah, you're coming through for now.
So I hope I don't want to say I hope it's the last virtual panel, because I'll be happy to have another one with you guys. But hopefully the situation worldwide is improving, and we have the opportunity to meet face to face and go do this type of panel live very soon. So hopefully. I think we're gonna end the recording, and I want to thank all of you again for your time, and looking forward to seeing all of you live soon.
Thank you.
Thanks, Jean-Marie.
Thanks.
For those panelists who are able to, if you can join into the virtual room, I'm sure there'd be people who would be very interested in talking to you.
Hi. Hello, can you hear me? Yeah. So, but we have some questions on the panel. We can address this later on, but we have Daniel on the panel. Daniel, you can answer from some of the questions from the panelists, from the audience, please.
Yes. Can you hear me okay?
Yes, Daniel.
Okay, so I believe there was a question to tie in that was about analog. So I won't try and answer that one because I've never been involved in analog, but the question about shift left, that's an interesting question. As we talked within the panel, we did mention we using IP models in order to reduce the amount of RTL that needs to be put into emulation or FPGA. So I think that's a good example of where you can get scalability by only including the RTL that you're interested in testing. I think shift left more generally is normally thought, or I normally think of it as sort of parallel development. So even if you're developing IP collateral using system models, a more shift left model would potentially be developing the RTL alongside that system level model and refining both in lockstep. If you think about, say, the case with classic hardware verification, where you don't wait to get your simulation well clean before moving to emulation or FPGA. You try and move to emulation FPGA earlier, even though that means you will find some bugs in emulation or FPGA that you would have found in simulation. And the next question I saw was whether scheduling or scalability issues should be solved through cloud solutions in the end. And I think I would agree that ideally these are problems that everyone is having to solve in order to use prototyping solutions. So having it solved in one place would make sense, but I think it is a different type of problem compared to just running large-scale financial compute or something like that, which you have a granularity that you need to deal with as well. Okay.
Thanks, Daniel. I hope it gives some answer to the questions. Regarding the question to Tai, we will reply it offline. Tai is not here for the moment. Any other question? Otherwise, we can capture them and reply later. Let's go for everyone. Okay, I think that we are good here. Thank you, everyone, and have a good DVCon Europe continuation.